Okay, everybody, today we're going to be looking at gravitational potential energy. Remember, this is the energy that an object has because of its height above the Earth's surface. So what I have here is an observation table that looks at the effect of mass and height on the gravitational potential energy of an object. So again, what we're looking at is we're looking at the mass and height affecting the EG. So we've got the two values here. You can see here that the table is divided into two components. The top part where the mass is constant and that the height is gradually changed. And we look at the effect on gravitational potential energy at the end here. We call it EG here. And then the second part where we change the mass, but we keep the height constant. And we look at the effect of mass on the EG value. So let's look at the first part here. So as I'm increasing my height, you can see here that my height goes from 0.5 to 1, or an increase of twofold. So twofold increase. When you look at the gravitational potential energy, it doubles as well. It's also a twofold increase. So you can see here there's some kind of relationship happening. We can also go back and say, okay, now what happens when I increase my height by a factor of 4? When we do that, we can see that my gravitational potential energy also increases by a factor of 4. So we can safely say is that the gravitational potential energy of an object is directly proportional to the height above the Earth's surface. Now in the second part of the table, we can see that we're changing mass. As we double the mass, the gravitational potential energy doubles as well, very similar to what we had before. And when my mass goes up by a factor of 4, my gravitational potential energy goes up by a factor of 4. So in other words, we have a direct relationship. So you can see that the gravitational potential energy is directly proportional to the mass of an object. And it makes sense. If you've got a small pebble or a large boulder, if they fall from an equal height, the boulder with the greater mass has more ability to do damage. It has more potential to do damage, more potential gravitational energy. Now what we're going to do is we're going to bring these two together, and we can see that gravitational potential energy is directly proportional to mass and directly proportional to the height. So based on this, we can develop an equation. So I'll go down here, and this is the note that you have in your workbook. So first thing we're going to do is to define what gravitational potential energy is. So remember, EG is the energy an object has due to its height above a reference point. We want to pick a reference point because we have to measure from some particular point. We'll talk about what this means in an example or two from now. And usually what we want to do with the reference point, you want to pick the lowest possible level. So do the lowest level. Okay, so now we've gone through that, what I can write down is the equation for gravitational potential energy. Now recall that the gravitational potential energy, again, was directly proportional to mass and height. So what I can do is then I can write the equation, EG is equal to m, and I'm going to have a constant here. The constant is going to be g, gravitational constant, and it's going to be multiplied by the height. So what we're going to have is the gravitational potential energy, so the change in gravitational potential energy, is equal to the mass of an object, so mass times the g value, which on Earth is 9.81 meters per second squared. And this is above the Earth, or above a reference point, so we're going to have a height associated with this. So there's my height. Now, if you remember, this is my equation then. So EG equals mgh. Now, remember that energy is measured in joules. It is a scalar quantity, so there are no directions associated with it. Mass is going to be measured in kilograms. G is meters per second squared. And we know that height will be measured in meters, just to be consistent from. And again, the question here is, where is the height measured from? The lowest reference point in most situations. So what we have here, just to kind of review, is again the relationships we introduced earlier. So direct relationship between EG and mass, and a direct relationship between EG and height. So based on those relationships, you can say that when you have the EG, when you increase the mass by threefold, because mass is directly proportional to EG, the EG would increase by a factor of 3. And similarly, when you increase the height by a factor of 3, the EG will increase by a factor of 3 because there is a direct relationship there. Okay, so enough of that. So again, basically the big thing here is that we have our equation. EG equals mgh. And this is going to give us the change in gravitational potential energy. All right, now that we've gone through that, let's look at an example. So what I have here is I want to know the change in gravitational potential energy for 75 kilogram skier skiing from point A to point B. So point A is 75 meters above the reference point. This is my reference point down here. And point B is 50 meters above the reference point. So I'm going to use the grasp method. So first thing I'm going to do is I'm going to write down my change in height. Now my height is going from 75 meters to 50 meters. In other words, I'm going to have a decrease in the height of 25 meters. So this is my decrease in height. There we go. Now my mass of the skier is going to be 75 kilograms. And I know my equation is EG, my change in gravitational potential energy, is equal to mass times G times my change in height. So in this case, my mass is 75 kilograms multiplied by 9.81 meters per second squared multiplied by my height. In this case, it's a negative value because I've decreased my height. And we plug the numbers in, we get a value of negative 18,394 joules. This negative, when you have a negative energy, it indicates you've lost energy. So negative equals loss of energy. In this case, we're losing our EG. So our therefore statement here would be, therefore, the skier loses, and I'm going to round this to 2 significant digits, 18,000 joules of gravitational potential energy. Okay? So most of the other examples are similar to this. We're going to actually skip this next little bit for later. Okay. So here's just a kind of recap of like a just conceptual basis, what's going on here. So you got an oil change, a car's lifted up, lowered to the ground, and we want to know the change in EG for each of the following components of its motion. So remember, the car was lifted up, and then it was lowered down back to the original point. So we have the reference point there. So when the car is being raised on the lift, it's going to go from point A to point B. It's going to gain EG. In other words, we're going to have a positive change in the gravitational potential energy. As we're lowering the car, you're going to lose EG, and we're going to have a negative EG change. And when you look at the whole situation going up and then back down, the car ends up at point A again. So for the whole up and down lifting motion, there is no change in EG. In other words, the EG change is 0. Okay? All right, so that's about it for gravitational potential energy. So now let's take a look at kinetic energy. Now kinetic energy is quite similar in that we're going to be starting with the relationship between the variables in the equation. In this case, we're looking at the effect of mass. Let me just use a different color here. So we're looking at the effect of mass and the velocity this time of an object on its EK. So how do these impact on the EK? So in the first component of the table, you can see that we're going to be controlling the velocity, and that my velocity in this case is going to go up by a factor of 2. Now, unlike the situation with gravitational potential energy, my EK does not double. Otherwise, it'll be around 0.12. In fact, when you look at the two values here, it looks like the EK has gone up by a factor of 4, which is quite interesting. I'm going to go back to the velocity here. Now my velocity goes up by 4. This, when you look at it on your calculator and you go 1 divided by 0.06, you get a value of around 16 times. So when my velocity goes up by 4, the EK goes up by 16. So let's look at this. This is a little mini table here. So when we have this, a twofold increase in the velocity, the EK goes up by 4. When my velocity goes up by 4, the EK goes up by 16 times. And you think about this, and you remember it's a squared relationship. So we can say that the EK varies with the square of the velocity, or v squared. Now, for the second part of the table, we're going to be looking at the effect of mass. So let's take a look at this. So when my mass doubles, if you look at the EK, it looks like the EK is doubling as well. It's going up by 2. And when my mass goes up by a factor of 4, looks like my EK goes up by a factor of 4. So for mass, there seems to be a direct relationship. It's directly proportional. So the EK is directly proportional to the mass. Now putting these two together, we can do this. The kinetic energy is proportional directly to mass and proportional to the square of the velocity, or v squared. So what we can do with this, we can change this into an equation. All right, so this is the note that you actually have in your workbook. It's on kinetic energy. So we're going to first define kinetic energy. So kinetic energy is the energy due to the motion of an object. So energy due to the motion of an object. All right, there we go. So it's motion. And when I look at the equation, my equation looks something like this. So the change in the kinetic energy is equal to 1/2 mass times my velocity, or sorry, speed squared. So directly proportional to mass and proportional to the square of the velocity. So this is my EK, my kinetic energy. This is going to be my mass, and this is going to be the velocity. Remember, the velocity is squared. So as before, this is my equation over here. We're going to measure energy in joules. That doesn't change. Mass is measured in kilograms, and my speed is going to be measured in meters per second. Actually, I should really have speed because, again, energy is a scalar quantity. So we should really have speed up here instead of velocity. Okay. Now, again, we know the relationships already, so know that EK is directly proportional to mass. We know that EK is proportional to v squared. So when I increase my mass by 3-fold, my EK goes up 3-fold. Again, directly proportional. When I increase my velocity, my EK goes up by square. So if I increase my velocity by 3, my EK goes up by 9, which is really important on the highway. So this is a note. So highway speeds. Most people recognize that when you double your speed on the highway, they think that you double the energy and the braking distance of a car. When in fact, what happens is your energy goes up by a factor of V squared. So your energy would go up by a factor of 4, and your braking distance would go up proportionally. So be careful. So when you're driving on the highway, if you're going, say, 50 kilometers an hour, if you're going at 100 kilometers an hour, you have to leave 4 times more space between you and the car in front. So again, just a friendly little tip, driving tip there to keep you safe. Okay, now we're going to be looking at an example using this particular equation. So here we've got a curling stone with a mass of 20 kilograms. It's sliding along the surface at 2 meters per second. I want to know the kinetic energy of the stone. Let's see what we have here. So I got my mass, which is 20 kilograms. I have my velocity or speed, which is 2 meters per second. And I want to know the kinetic energy. And the kinetic energy is equal to 1/2 the mass times the speed squared. So we're going to plug our values in here. So we have 1/2, don't forget about that, 20.0 kilograms times 2.0 meters per second. And don't forget this, it's squared. Very, very common mistake is to forget this part of the equation. So don't forget the square there. All right, then when you plug the values in there, you're going to get a value of 40 joules. So therefore, the curling stone has 4.0 times 10 to the 1, remember 2 significant digits, joules of kinetic energy. All right, let's do a little bit harder example. So in this situation, I have a 10 kilogram stone. If it had the same amount of kinetic energy, how fast would it be traveling? So my mass here would be 10 kilograms. My EK now would be 40 joules. And I want to know how fast would it be going, my speed. So like before, I've got my equation, 1/2 mv squared, except now we're solving for the speed. So we're going to just rearrange the equation. So 2ek, and multiply both sides by 2, divided by mass is equal to v squared. So let's plug some numbers in here. So 2 times 40 joules all over 10 kilograms is equal to v squared. So 2 times 40 divided by 10, so it's 80, don't think too hard, divided by 10, which is 8. So my speed is going to be the square root of 8. And that ends up being 2.8 meters per second. So therefore, the curling stone's speed would be 2.8 meters per second. So a little bit faster than we had before. Because again, less mass, same energy, means we're going a little bit faster. All right, we're going to omit this last little bit for now, and we're going to go back to the other handout, the EG handout, just for a little bit. Remember here, we had a situation where I had a skier going down a hill, and as they went down the hill, they lost their gravitational potential energy. Well, we know that energy has to end up somewhere. So this lost energy over here, this value, where are we here? Sorry. This value over here, 18,394 joules of energy must end up, and what happens is, you think about it, it ends up as EK. You begin to move and speed up as you're going down the hill. So if the gravitational potential energy was completely to convert to kinetic energy, how fast would the skier be traveling at point B if starting from rest? So here's what we know. I know that my EK is going to come from my EG loss. So the loss of EG is going to equal to the gain in EK, and then that's equal to 1/2 mv squared. So if you recall, the loss of EK was 18,394. So that's going to be how much EK I gain. My mass here is the same as before, 75 kilograms if you recall. And I'm going to be solving for speed, very similar to what I did before. So now, when I plug my numbers in, we're going to end up with a value of 22 meters per second. So, little therefore statement. Therefore, the skier would have a speed of 22 meters per second, 2 significant digits, at point B. And that brings us to the end of our lesson. Hopefully you had a little bit of fun going through EG, EK. Enjoy doing these sample problems or the practice problems.